Hello YouTube. In this video I'm going to introduce the problem of scientific progress. It seems obvious that science has exhibited progress in some sense. Of course, judgments of progress are subjective, or at least I would say they're subjective. They're going to depend on what it is we value about science or what we think the aims of science are. Still, there have clearly been substantial changes in science over the last few hundred years, and I think most of us would say that these are changes in the right direction. So what exactly is scientific progress? I'll go through a few suggestions in this video, and this is based mainly on Alexander Bird's article in the Oxford Handbook of Philosophy of Science. Bird identifies three basic views of scientific progress. First, the problem-solving view, which says that science makes progress when it solves scientific problems. Second, the semantic view, which says that science makes progress when it gets closer to the truth. And finally, the epistemic view, which says that science makes progress when it increases our stock of knowledge. Now, you might already have a sense of where different philosophers might fall on these issues. If you've seen my videos on scientific realism, you can probably guess that anti-realists might be more inclined to the first view because that doesn't rest on supposing that science increases truth. So, you know, that might be appealing to an anti-realist. So let's consider these in a bit more detail. We'll start with this first idea that scientific progress consists in solving scientific problems. I think this is reasonably intuitive. The thought is that particular scientific traditions give rise to certain problems, usually in the form of a contradiction or some sort of other tension between theory and data. You know, we find that the data doesn't quite fit the theories we have. Scientists then work to solve these problems. They work to bring their theories into closer agreement with the data. And progress consists in solving these problems. There are all kinds of examples we might appeal to here, but consider that shortly after the discovery of Uranus, its orbit was found to deviate from the predictions of Newtonian mechanics. So what we want is a solution that makes the orbit of Uranus derivable from Newton's laws and that has observational consequences that are empirically confirmed. The proposal of an eighth planet having gravitational influence on Uranus seems fairly obvious, and that was of course confirmed because you can see that eighth planet through telescopes. Another example is that in the mid-1900s, estimates of the age of the Earth based on radiocarbon dating gave about 3 billion years, while estimates of the age of the universe based on the rate of expansion given by Hubble's laws were only 1.8 billion years. This was resolved when astronomers realised that in working out the rate of expansion of the universe, Hubble had underestimated the luminosities of different stars, of distant stars. And so that they then recalibrated the distance, and that recalibrated the rate of expansion, which then gave about 10 to 20 billion years for the age of the universe. So that was a kind of tension between two theories was resolved. One obvious benefit of viewing progress as problem solving is that it doesn't appeal to difficult metaphysical concepts like truth. I mean, it seems that it will be much easier to determine whether scientists have solved a problem than whether they've found the truth. Still, there is a question here of, well, what counts as solving a problem? Bird discusses here the views of Thomas Kuhn. I have a video on Thomas Kuhn in my Philosophy of Science series, which you should watch if you're not familiar with Kuhn. But briefly, Kuhn's foundational claim is that scientists in a particular field adopt what he calls a paradigm. A paradigm is a kind of worldview. It specifies the basic features of the world. It tells scientists what kinds of questions are to be asked about the world. It specifies certain experimental and theoretical techniques for answering questions, and it supplies the standards for what counts as a good answer. All the scientists in a particular field adopt the same paradigm, and this allows them to work cooperatively in a highly organised structure. And because there is general agreement on what the world is like and how to research it, this allows scientists to focus in great depth on specific issues. And so that explains why science provides such deep understanding, such deep and precise knowledge. Paradigms are built around problem solving, In particular, paradigms include what Kuhn calls exemplars. Exemplars are solutions to specific problems that are then taken as models for further research. So the scientist learns to see other problems as relevantly like the exemplar. Consider, for example, Mendel's experiments on pea plants. For a long time, the tradition of classical genetics solved problems by attempting to emulate Mendel's style of research, but in different organisms. So when all scientists are united under one paradigm and they all approach scientific problems in the same way, this is normal science. This contrasts with what Kuhn calls revolutionary science. So all paradigms face anomalies, right? There are going to be problems that can't be solved in terms of the prevailing paradigm. And the thought is that as anomalies accumulate, scientists begin to lose confidence in the paradigm. This leads to new paradigms being proposed and ultimately to a scientific revolution, where one paradigm is replaced by another. Think of how Aristotelian mechanics was eventually replaced by Newtonian mechanics, and then Newtonian mechanics was replaced by Einsteinian relativity. These changes involved huge shifts in how scientists saw the world. So the thought then is that during normal science, progress is a fairly straightforward matter. We find that as a paradigm develops, increasing numbers of problems are solved. Revolutions are a little bit trickier because paradigms give scientists guidance as to what problems they should be concerned with, and paradigms supply the standards of evaluation. So if a paradigm changes, problems that were once regarded as solved may become unsolved, or problems for the earlier paradigm will simply disappear in the later one. For example, Bird points out that Descartes had a kind of vortex theory of gravity. Now, we don't need to go into the details here, but Descartes held that all of space is filled with a very fine matter, and this tends to form circular motions, and these swirling vortices are responsible for gravity. Now, Descartes' theory explains why the planets all orbit in the same plane, and they all have the same direction of rotation. Newton's theory of gravity is far more powerful than Descartes' in many respects, but it doesn't solve this problem, or at least it didn't when it was first proposed. So in this case, we see that a problem solution was lost, right? In this particular respect, there was a reduction in problem-solving ability when Descartes' theory was rejected in favour of Newton's. This loss of problem-solving ability is often called Kuhn loss. As an example of problems that just disappear, consider Ptolemaic astronomy, which held that the Earth is the fixed centre of the universe, and the stars are embedded in a crystal sphere that rotates around the Earth. This view of the cosmos raises various problems. So we might ask, well, what are these spheres made of? What is their geometric structure? What drives their motion? And so on. With the Copernican revolution, these problems, well, they weren't solved, right? They just disappeared. They just weren't problems anymore. They were simply inapplicable. So the point is then it's kind of difficult to compare the problem-solving ability of the Ptolemaic theory with that of the Copernican theory because they had different problems. Now it's clear that if we want to say that science in general progresses, then it must be that each new theory solves more problems than its predecessors. But the kinds of cases just discussed show that science isn't simply cumulative in this respect. So we're going to need some way of counting problems, and then we need some way of weighting them because some problems will be more significant than others. And how do we do that in a kind of objective way? Kuhn himself simply accepted that there is no objective way to do this. Kuhn said, look, paradigms supply the standards of evaluation. There's not going to be a completely independent way to measure progress. And I think this may be a bit of a problem insofar as one benefit of the problem-solving account of progress was its supposedly greater clarity, because it doesn't require appealing to these vague concepts such as truth. Well, if it turns out that we actually have no clear independent way of measuring problem-solving ability over time, then actually it looks like the problem-solving view doesn't really do any better. It's not really all that clear. It seems to be quite murky on how to actually measure progress. Another objection to the problem-solving approach is that it seems to entail that there are cases where rejecting a false theory counts as regressive. Bird gives the example of research into N-rays. In the early 1900s, the physicist Prosper René Blondlot, a name that I'm probably not pronouncing correctly, so apologies for that. Anyway, this physicist claimed that he had discovered a new form of radiation. He fired X-rays through a quartz prism, which was known not to reflect X-rays, and he had a detector off to the side that produced an electric spark when radiation entered. Now, he noticed that the spark in the detector was brighter when he fired the X-rays at the prism, which suggested that radiation had been reflected off the quartz. But as I said, this couldn't be X-rays, because the quartz doesn't reflect X-rays. So it must be something new. It must be some new form of radiation. He called it N-rays. Over the next couple of years, a whole research tradition grew out of Blondlot's experiments. Numerous scientists studied N-rays and explored their properties, and hundreds of papers were published. Theories about them were proposed, new means of detecting them were developed, but some scientists just couldn't detect them at all, which is quite natural. When there's a new phenomenon in science, a new kind of observation has been made, it can be very difficult and technical to get the experimental apparatus right. But still, there was a sort of skepticism beginning to grow. Then in 1905, the physicist Robert Wood went to Blondlot's laboratory and removed parts of his equipment without telling him. Blondlot still claimed to observe the N-rays. So it became pretty clear that N-rays didn't really exist. They were some sort of subjective illusion. Now, the crucial point here is that it's not that some new theory of N-rays was proposed. Research into N-rays simply stopped. So here we have a case where there was a research tradition which created and solved problems. So this was progressive on the problem-solving view. And then as a result of Wood's investigation, the problems and solutions were lost without any new theoretical development. So that would seem to count as regressive. But that surely is wrong. Surely Wood's investigation was a clear case of progress. A similar example is maybe the rise and fall of introspective methods in psychology. So in the late 1800s, psychologists became interested in learning the details of conscious experience. And you do this by introspection. This method involves, so you might expose somebody to a particular stimulus, say a bright flash of light, and then you have them attend closely to their immediate mental phenomena and describe in great detail, but in a neutral manner, what they observe. You run this experiment hundreds of times and try to capture every detail of the phenomenology of the after image. And there were strict methods developed for honing your ability to introspect and for reporting introspective judgments. It was hoped that these observations of immediate conscious experience would provide a kind of base of data on which to build a truly scientific psychology. Unfortunately, there were different schools of psychologists, and it turned out that they all described their experiences in different ways. The introspective method just failed to achieve a consensus on what the data was. And this, of course, led to the rise of behaviorism, which argued that psychology should avoid any reference to conscious experience, purely internal, it should avoid any reference to the purely internal mental states and focus just on behaviour. Again, in this case, a whole tradition of research was eliminated, and no new theories were proposed for the problems or the observations with which this earlier tradition was concerned. The behaviourists simply looked at other things. You might say they simply changed the subject of psychology. So it seems that the rejection of introspective psychology, again, has to be considered regressive. but that doesn't seem right. It was rejected for very good reasons. Now, so this is a problem that Bird raises for the problem-solving view. I think that actually there's kind of an obvious response to these cases. We might say, well, the rejection of a whole base of empirical evidence is itself a problem solution. And in fact, it's a very significant solution insofar as it has substantial consequences for science. The consequence is the rejection of an entire domain of research. Fundamentally, the problem posed by N-rays, for example, was explaining certain observations. Scientists were making observations in their laboratories which didn't fit with any known theory. And one solution for this, which they initially went with, was N-rays. And then you have to distinguish different types of N-rays and different ways of producing them and so on. But then another solution, another way of making those observations compatible with theory, is to show that the observations are illusions. This is a very powerful solution because it immediately solves all of the problems of the domain. So I think perhaps that Bird has too narrow a conception of what's involved in solving problems. And this is why the rejection of N-rays can be progressive. Still, I think that this doesn't fully answer Bird's concern, because another part of the problem that Bird raises is that it seems that on the problem-solving view, research into N-rays and research in introspective psychology would count as progressive as long as problems were created and solved in those traditions. So there was a 2-year period where scientists took N-rays seriously and they seemed to solve various problems about them. And it looks like that has to be considered 2 years of progress. More intuitively, I think we'd say that there was just no progress in this case. Scientists were simply misguided, and ultimately the research into N-rays was really a waste of time. But it looks like the problem-solving account has to say that was progressive. So maybe there's still an objection to be raised here. Okay, let's turn to a different view. The second account of progress is known as the Semantic View, and this claims that progress consists in increasing nearness to the truth, or verisimilitude. This is a technical term meaning truth-likeness, close to the truth. So it said that science exhibits increasing verisimilitude. As science develops, theories get closer to the truth. Maybe we'll never know the whole truth, but we do get closer to it, and that's what progress involves. An immediate question that is raised here is with this idea of truth-likeness or approximate truth. We might understand what it means for a statement to be true, but what is truth-likeness? What is approximate truth? I have to say, yes, this is sometimes sort of raised as a serious kind of objection that we maybe don't have a coherent concept of approximate truth. I don't really see this as much of a pressing issue, just because it seems to me that the concept of approximate truth is perfectly commonsensical. It's not some technical philosophical device. Of course, that doesn't mean that it's without problems, but I do think we have a perfectly good idea of what's trying to be said here. So, suppose there are 102 balls in a jar. I say there are 100 balls in the jar. You say there are 90 balls. Neither of us is exactly right, but I'm closer to the truth than you are. As a scientific example, Bird gives the estimates for the value of Avogadro's constant. So assuming that we now have the right value, then we can say that Rutherford's estimate was closer to the truth than Perrin's estimate. And that's, I think this is I think this is a fairly straightforward idea. Now this view, the semantic view, is certainly intuitive. I think we do think that as science develops, it generates more truth or gets closer to the truth. But there are still a few problems here. A first worry is that it seems that science could be made closer to the truth simply by jettisoning those theories we regard as less well developed. We might think that physics, for example, is especially powerful and especially well confirmed. So physical theories are very close to the truth indeed. On the other hand, something like psychology, well, this is still a young science. There's still much work to be done, so maybe we're on the right lines and we've revealed some truths about the mind, but overall psychology is only going to vaguely approximate the truth. So, just as a sort of visual example, if we have the truth about physics here and the truth about psychology here, current physics is sort of closer to that than current psychology is to the truth about psychology. Now, clearly, if you think about the amount of truth on average in science as a whole, we could move science closer to the truth simply by eliminating psychology from the domain of science. So in the same way, we just eliminate all sciences that are less than the best. Another concern is, consider the claim that Avogadro's constant is approximately 6.7 times 10 to the minus 23. That's not this is true, right? It's not near the truth. It's just true because we've built the approximation into the claim itself. So this claim isn't false in any respect because the claim already allows for variation. It shouldn't be interpreted exactly. Now, if you were to replace this with Avogadro's constant is 6.022 times 10 to the minus 23, that would seem to constitute progress, but it doesn't take us anywhere nearer to the truth because we already had truth with the original claim, the original Vega claim. So what these two problems suggest is that progress isn't just a matter of getting closer to the truth, we also need informativeness. As science develops, we expect it to tell us more. A more precise claim, as in the Avogadro example here, that is more informative. It doesn't necessarily increase truth, but it does give us more information. A third problem with the semantic view noted by Bird is that there are many cases where science increases the number of true claims, but where we wouldn't say it exhibits progress. He gives the interesting example that in the Renaissance, doctors accepted the humoral theory, which held that the human body contains four humours: blood, phlegm, yellow bile and black bile, and diseases are caused by imbalances in the humours, with specific symptoms being caused by specific imbalances. Furthermore, these bodily humours were associated with basic qualities of matter, as shown here. So your blood is moist and warm, yellow bile is dry and warm, and so on. It was additionally believed that the natural balance of humours in the body changes with time. As you grow, the relative proportion of yellow and black bile increases, so the body loses moisture. And this explains why elderly people are wrinkly, whereas babies are soft and smooth. There is more moisture in the babies. Today, of course, we think that the humoral theory was totally mistaken, but it turns out that they were right, that the proportion of body water declines with age. That is something that happens. So, in this respect, the humoral theory led to increased truth. Presumably, though, we wouldn't want to say that this was progress. A similar example is that Johannes Kepler had a rather bizarre theory of the solar system. He thought that it had been arranged by God to fit certain geometric facts. So obviously it was known that the Earth had one moon, and then when Galileo discovered the 4 moons of Jupiter, Kepler reasoned that Mars must have 2 moons, because this would produce the right mathematical series. Of course, Jupiter actually has dozens of moons, but in Kepler's time, they thought it was 4. Kepler came to this conclusion on the basis of a bizarre theory, but it actually turns out he was right. Mars does have 2 moons, Phobos and Deimos. If Kepler had managed to persuade other scientists that Mars had 2 moons, again, you wouldn't want to call that progress, but it would have increased truth. So this leads us to the third account, which is known as the Epistemic View, and this says that progress consists in increasing knowledge. What was missing for the Renaissance doctors and for Kepler is knowledge. They had true beliefs, but these beliefs weren't justified in the right kind of way to count as knowledge. There's more to knowledge than just true belief. There needs to be the right kind of justification. I won't go into the many different theories of knowledge here, but the point is you need the right sort of justification beyond just having a true belief. The Renaissance doctors who claimed that infants have a higher proportion of body water were right by luck, basically. It just so happened that a totally defective theory led to the right result in this particular case. So on this epistemic view, science at its best gives us knowledge. It gives us true beliefs that are properly justified. And increasing knowledge is what constitutes progress. And again, as with the other views, I think this is reasonably intuitive. There are many ways we might come to have knowledge of the world. It does seem that one of the most important is through scientific research. Now, Darrell Rowbottom, in his article Scientific Progress Without Increasing Verisimilitude, presents a problem for any model of progress that ties progress to truth or knowledge. Suppose that at some future time, scientists believe they have achieved a true general theory for their domain. And suppose also that this belief is correct and justified. There really is no more for them to discover. These scientists have achieved the maximum amount of knowledge. On both the semantic and epistemic view, it seems that no further progress is possible. Scientists working in this area should just stop and move on to other fields. But Rowbottom objects that progress is still possible. For one thing, the true theory might be extremely complex and unwieldy, impossible to use in practice, so we can't make predictions or design technology using that theory. In that case, scientists could make progress by working on simplifying the theory, or even by developing false theories that are easier to use. Consider how we still use Newtonian mechanics in many contexts, or how Ptolemaic astronomy is still used in navigation. In general, when doing science, we appeal to models which involve approximations and idealizations. Rowbottom gives the example that if you have a pendulum and you want to predict and explain its motion, the complete theory of the pendulum will specify the precise details of the initial conditions, so the exact heat of your hands when you hold it, plus the exact air resistance it encounters as it moves, and so on. But this will be an extremely complex model. We probably wouldn't be able to learn much about anything from it. What we need is a model that abstracts away from various factors and that tells us only about the important features of the physics of the pendulum. And notice that's just the motion of a pendulum, which is an extremely simple system. Compare that with models in ecology, when we try to model predator-prey relationships or patterns of ecological succession. It's clear that if we want a general theory of predator-prey interactions, if we want a theory that will be useful for making predictions and will increase our understanding of the world, we're going to need to simplify and abstract very substantially from the specific details. So it seems that we can achieve progress by promoting theoretical virtues beyond just truth and knowledge. Now, I think this is a fairly decisive criticism of the semantic view, but defenders of the epistemic view can respond that Rowbottom's criticism depends on too narrow a view of knowledge. Moti Mizrahi, in his article What is Scientific Progress? Lessons from Scientific Practice, outlines a more robust view of knowledge by considering what scientists themselves have had to say about progress. In particular, he examines Karl Landsteiner's discovery of blood groups, for which Landsteiner was awarded the Nobel Prize. Mizrahi quotes the Nobel speech on why Landsteiner's work was so important. They say, Landsteiner's discovery of blood groups has opened up new avenues of research in several branches of science and has brought with it important advances in the purely practical field. They continue, In the field of genetics, the discovery of blood groups has proved to be of importance from the point of view of methodology in the study of the hereditary transmission of other characteristics. So the discovery of blood groups had significant practical applications in medicine. Before we knew about blood groups, many blood transfusions failed due to blood clumping. This was initially believed to be a pathology, but Landsteiner showed that it was an immunological reaction, and his work allowed the development of successful blood transfusion. Landsteiner's work also involved the development of new experimental methods, for example certain purification techniques, and it opened up possibilities for further research in other areas of science such as genetics. Now, when philosophers think about science, they tend to be very concerned with things, with the theory, and then with the truth of theories and so on. That's probably because philosophers are themselves more inclined towards theory than to more practical results. So when we think about scientific progress and scientific knowledge, we tend to emphasize these theoretical aspects. But there are many different types of knowledge. Mizrahi identifies 4 types of knowledge that are promoted in science. First, there's empirical knowledge. And this just refers to experimental and observational results. For example, the observation that blood transfusions can lead to blood clumping. Second, there's theoretical knowledge, which involves developing well-confirmed models and hypotheses. So this is knowing that blood clumping is an immunological reaction, not a pathology. That's theoretical knowledge. Third, there's practical knowledge, which just involves practical applications of the theory, such as knowing how to determine different blood groups, knowing how to carry out blood transfusions safely. Finally, methodological knowledge. This refers to the methods and techniques for studying nature, such as knowing how to purify antibodies to study immune responses. Now, these first 2 types of knowledge are propositional knowledge, or knowledge that. We have propositional knowledge when we know that some proposition is true. Knowing that blood clumping is an immunological reaction is propositional knowledge. But there's also more practical knowledge, or knowledge how. Just as we say that a person knows how to ride a bike or knows how to play an instrument. Knowing how to ride a bike is a practical skill. It's not a matter of knowing some set of propositions. Mizrahi's point is that scientific progress also involves knowing how, not just knowing that. In Rowbottom's scenario, scientists have achieved maximum propositional knowledge, but they can still aim to attain greater know-how. So by adopting a broader view of scientific knowledge, the epistemic account can accommodate Rowbottom's critique, simplifying a true theory and so allowing for predictions and practical applications. This would increase know-how. An interesting point to note about this view of progress is that it makes the epistemic view compatible with anti-realist approaches to science, because anti-realists are perfectly happy to accept that science increases our practical skills and abilities. Of course, because this is such a broad conception of knowledge, it may be difficult to identify when knowledge increases. But then, the problem-solving view had a similar issue. It's difficult to identify increases in problem-solving ability. Maybe this kind of thing is a feature, not a bug. After all, scientific progress is quite complex and messy, and it can be difficult to identify when progress obtains. Anyway, that was a bit of an introduction to some of the views of scientific progress. That's all for today. Thanks for watching.